Hello everyone, my name is Spencer Camacho, and for this summer 2021 Advanced Musical Acoustics course, I will be presenting my final project titled Move in Progress, Exploring Studio Apartment Acoustics. For those exploring the field of musical acoustics for the first time, the world can feel overwhelmingly expansive. Young acoustic engineers typically find themselves attempting to treat an apartment bedroom with the desire to make it as reliable as a professional studio. This first experiment tends to fall short, with results showing a lack of success. This project, in contrast, explores the acoustic properties of a unique studio apartment shape, size, and overall space, all while slowly bringing in large pieces of furniture. While the experiment like this may not provide groundbreaking research, it is a topic worth addressing for novice acoustic researchers. This is because the experiment shows how a relatable recording space, such as an apartment, is modified by common furniture by starting with a completely empty space. Working from a blank slate isolates the room attributes such as its size, dimensions, and construction materials, which become the control variable when exploring the acoustic changes when modifying the space. It is important to note that the goal of this experiment is not to create the flattest sounding room, but to explore how a room's contents can alter its acoustic properties. With this goal, an impulse response is taken with each alteration of the studio apartment, with the first impulse response taken while the apartment is empty. Here is a generated diagram of my apartment. Setting up the experiment, I started by placing a Yamaha HS8 monitor 6 inches out from the corner of the apartment, exactly 5 feet above floor level. The HS8 pointed directly at the corner of the room diagonally opposite, where a biodynamic MC930 small diaphragm cardioid condenser microphone stood. The MC930 pointed back at the HS8, also 6 inches from its respective corner and 5 feet above floor level. Both HS8 and MC930 connected to a Scarlett 2i2 interface and a MacBook Pro, which rested on the windowsill of the apartment's east wall between them. The height of the entire space is 7 feet. I then played a sine suite generated by the Room EQ Wizard through my preferred digital audio workstation, Logic Pro, and recorded the sine sweep with the MC930 while in the kitchen to avoid standing between the HS8 and MC930. Here's what Impulse 1 sounded like. For my second impulse response, I added a 7 by 10 foot rug in the corner of the room. Here's what Impulse 2 sounded like. Next, I added a second 7 by 10 foot rug next to the first rug, overlapping 10 inches. Here's what Impulse 3 sounded like. Next, I added a couch against the east wall. Here's what Impulse 4 sounded like. Finally, I brought a variety of miscellaneous items into the room. Here is what Impulse 5 sounded like. After exporting the impulse responses from Logic and importing them into the Room EQ Wizard, I exported the impulses as WAV files. Here are the 5 impulse responses played back to back. When looking at the RT60 graph generated in the Room EQ Wizard, the lines representing the impulses are labeled by color, which are listed below the graph, the highest in red being the empty room, working down to the light green line when the room was most filled. Being an RT60 graph, the y-axis resembles the time in milliseconds a particular frequency decays, while the x-axis depicts the said frequency in hertz. The most noticeable resonant frequency in the space when the room was empty was the large red spike at 250 Hz at 2.4561 milliseconds decay. Since the apartment is at ground level, behind the drywall is cinder block. The ground floor is a vinyl tile on a concrete slab. With this knowledge, one can decipher the absorption coefficients. While the floor remains relatively consistent, the reflective wall material being concrete and any plywood paneling within the drywall are at their highest sabins at 250 Hz. Other than this large spike, there are 4 relatively small attenuations at about 200 Hz, 400 Hz, 800 Hz, and 250 kHz. In contrast, the spike at 78.5 Hz, 156 Hz, and 3.11 kHz are all spikes in decay time, relatively high compared to their RT60 response. Overall, this experiment presented a space with relatively limited variance, being the material of the floor and walls. Introducing each new piece of furniture provided data for comparing the impulse responses, generating the RT60 graph. By referring to absorption coefficient charts, points of resonance and attenuation correlated with the response in the room. While there is much more which could be gleaned from the resulting data, this first look into this apartment's RT60 provided researchers new to acoustics a foundation to understanding and interpreting resonance in a space.